Okay, the 2013 differential equation question says consider the differential equation dy dx equals y squared times 2x plus 2, let y equals f of x be the particular solution to the differential equation with the initial condition f of 0 equals -1. It's actually a very similar start of a problem to the last one, the 2009 one. So we start with a question that we really wouldn't expect to see on a differential equation question. It is asking us to evaluate a limit as x approaches 0 of f of x plus 1 over sine of x. So anytime we have a limit, we always want to plug our value in. So to evaluate this, we would do f of 0 plus 1 over sine of 0. Well, sine of 0 is 0, and f of 0, they tell us that initial condition is equal to -1. So we get -1 plus 1. This is that indeterminate form which requires us to either manipulate it or do L'Hopital's rule. And so that's going to be the easiest way to move forward here. Once we do L'Hopital's rule, we'll again take the limit, but we're going to do the derivative of the numerator and the denominator. The numerator derivative will just be f prime of x, and the denominator will be cosine of x. When we plug in 0 here, we've got f prime of 0 over cosine of 0. Now cosine of 0 is super easy to evaluate, that's just going to be 1. But for f prime of 0, to evaluate that, we have to actually look at our derivative. And we have to evaluate our derivative dy dx at the point 0, -1. Because the 0 is our x value. But since our derivative is in terms of x and y, we need to make sure we have the whole point 0, 1. Or 0, -1. So that will give us -1 squared times 2 times 0 plus 2. And, oops, didn't need that. And that gives us a value of 2. So we get 2 over 1, which means the limit value is equal to 2. This is a 2-point question. We get 1 point for using L'Hopital's rule. So getting to this is a point, and then getting our final answer of 2 is a point. So 2 points for part A. Part B. Question B is an Euler's method question. We've been a lot of practice on Euler's method. We're going to make our table up x, y, y prime, delta x. Delta y equals y prime times delta x. And we start with our point 0, -1. And we're going to use Euler's method with 2 steps of equal size to approximate f of 1/2. So if our goal is to get up to 1/2 in 2 steps, we definitely need to have a middle step where x is equal to 1/4. We want to find the y value when x is equal to 1/2, and our delta x to get up to that 1/2 is going to be 1/4. If you want to use 0.25 instead of 1/4, it all is good. Just go for it. So now on to Euler's method. We're going to take our first point, 0, -1. We're going to plug it into dy dx. In part A, we had to do the derivative at 0, -1. We got that value to be 2. So now we'll take 2 times 1/4, and that's going to give us 1/2. 1/2 will be added to -1, which will give us a -1/2. And now we'll plug 1/4 and -1/2 into the derivative. So I'll do that work up here. dy dx at the point 1/4, -1/2. What we are left with is -1/2 squared times 2 times 1/4 plus 2. -1/2 squared is equal to +1/4. 2 times 1/4 is 1/2 plus 2, which leaves us with 2.5 or 5/2. And if we multiply that out, we get 5/8. Okay, so we've got 5/8 times 1/4. So our delta y is 5 over 32. And then we've got negative 1/2 plus 5 over 32. We may need to do a little work on this side here. Negative 1/2 plus 5 over 32. We'll find a common denominator. We'll write this as negative 16 over 32 plus 5 over 32. That gives us a value of negative 11 over 32. So our solution, our approximation, is that f of 1/2 is approximately equal to negative 11 over 32. And again, Euler's method question is going to be worth 2 points. A point for the work and a point for the final approximation. So 2 points for part A, 2 points for part B. That leaves 5 points for part C. It's a question asking us for a particular solution. This is an indication that we need separation of variables. In order to use separation of variables, we first have to have our derivative written as a product. And our derivative is written as a product here. So we've got y squared times 2x plus 2. So our first step is to separate, and that's our first point. We'll get dy divided by y squared equals 2x plus 2 dx. Now we will integrate both sides. So that separation, by the way, that is 1 point for just that separation. Now to do the antiderivative, we need to think about this as y to the negative 2. So when we do the antiderivative, we're going to get y to the negative 1 divided by negative 1, which just gives us a negative y. Antiderivative of 2x is x squared. Antiderivative of 2 is 2x plus c. Both antiderivatives are, so if we have all that correct, that's a point, and then our constant is a point. Now we want to solve for y and then solve for c. I want to get rid of this negative right away, so I'm going to rewrite this left side. First thing I'm going to do is rewrite it as 1 over y, and I'm going to move the negative to the right side. So we're going to get negative x squared minus 2x, and we're just going to leave a plus c that's going to take care of itself later on when we actually go to solve for c. Now, if I want to solve for y here, and I've got 1 over y equals all of the right side, think about multiplying by y on the right side and dividing by all of this right side. And we're going to get y equals 1 over negative x squared minus 2x plus c. So that's solving for y. Now I want to find my c value. So I need to use the initial point of 0, negative 1. When we do that, I'll plug in negative 1 for y, and we'll get 1 over negative 0 squared minus 2 times 0 plus c. What this tells me is I've got negative 1 equals 1 over c, which implies that c is equal to negative 1. So our final solution is y equals 1 over negative x squared minus 2x minus 1. And that is our final solution. So point-wise, our final solution of y equals is a point, and then plugging in 0 to 1 to solve for c is also a point.